Moving away from the broader philosophical questions and argumentative questions that surround notions of representation, we're going to look now at how patterns are taken to represent within neural networks. A first important distinction is between means of encoding the world, in which we use a bunch of units, and the unit is on if a feature is present in the world or is off when the feature is not present in the world. In the extreme case, we have a bunch of mutually exclusive patterns, shown here as localist encoding, where we have, 8 input units, and each pattern has only one bit on, and so these 8 patterns will stand for 8 things in the world. That's one way of establishing a correspondence between elements in our modeling vocabulary and elements in the world. Notice that there is no attempt to capture similarity relations in the real world under such a scheme. At the bottom, I've shown on the left-hand side how this would look for 3-dimensional input vectors. You can see that there would only be 3 such vectors at points 1, 0, 0, 0, 1, 0, and 0, 0, 1, respectively. That's a very, very constrained kind of encoding, and it permits no semantic structure of the world to feature in the input patterns. Far more common in neural networks is the use of distributed encodings. Here, I've shown you a couple of other 8-bit vectors, and you can't interpret these directly, but if each of these stands for variation along 8 dimensions, continuous variation along 8 dimensions, then we have a rather different relation between our patterns and the world. For the 3-dimensional case shown below, you can see 3 points now at an arbitrary location within a 3-dimensional space. This kind of maximally distributed representation allows us to include some kind of similarity among elements in our data set that stands in correspondence to similarity relations among things in the real world. And later on we'll see that such highly distributed representations have certain properties that neural network modelers have valued over the years. And between these two extremes, we have several other options available to us. So in the strictly localist representation, one unit corresponds to one thing. So there may be digits, or behind all this is the idea that an individual computational unit might represent on its own something out there in the world. You may have heard of the famous grandmother cell, a hypothetical neuron which would respond only to a presentation of your grandmother's face. A fiction, but inspirational nonetheless. In distributed representations, many units correspond to one thing, and one unit is affected by many. It is involved in the encoding of many things. These become harder for human beings to parse. They are more strictly numerical. And distributed representations will occur as a matter of course at the hidden layer, where we don't dictate what values the hidden units take on, rather they compute their values. When we encode some properties of the world using distributed representations, then each individual unit can be said to correspond to one featural dimension, or one feature of an element in the problem domain. It doesn't correspond to a whole entity or a thing. Just by the by, the distinctions we're making here really apply in the interpretation of data within feed-forward networks. When we get to recurrent neural networks, the same question will appear slightly differently, and there our question will be not have we captured the right features, but how rich is our state description. We'll get back to that later. Now, coming back to that limiting case of an extreme localist representation. If we have a 3-dimensional input vector, and there's only 3 possible vectors, some of which are shown there, you can see that given any pair of those vectors, we can measure the distance between them, But for all pairs in our set, that distance is going to be identical. The formula given there for Euclidean distance is the familiar idea of the distance between 2 points on a line, taken now more generally to represent the distance between two vectors. We take the pointwise Euclidean or straight line distance between them, sum it up and take the square root. That's known as the Euclidean distance between 2 points. Here, all pairwise distances will be the same. In the more general case of distributed representations, this Euclidean distance becomes somewhat more meaningful. This provides us with a way of saying whether two vectors in our set are highly similar or highly dissimilar, and whether a group of patterns cluster around a specific set of values or don't cluster around a specific set of values. So the Euclidean metric is a very common way of describing similarity relationships between elements in our data set, training set or output set. Those similarity relations do not transfer unproblematically to similarity relationships in the real world. There, the degree to which we have successfully picked out the relevant features in order to make a domain intelligible is going to be important. In other words, that's our responsibility. For distributed representations, however, we can make sense of the notion of two patterns being very similar or very dissimilar. Sometimes we encounter this particular mismatch in which each element in a vector is 1 or 0, but we don't have the extreme limiting case of just one bit being on. This is a constrained form of distributed representation. Here, I've shown the 8 corners of a cube there, slightly warped, sorry. Here we can make some sense of the notion of distance between two elements. And in this highly constrained representation, we would probably not choose to use the Euclidean metric, which generalizes to three-dimensional space. Here, if all the data elements are constrained to lie at vertices, corners of a hypercube, then there are simpler distance measures like city block or Minkowski distance. So, for example, if you consider first of all the element at the bottom left-hand corner of this cube, it is 1 city block distance away from 1, 2, 3 elements. It is 2 city block distances away from 3 elements, and it is 3 city block distances away from the diagonally opposite corner. So this is a much more constrained form of distributed representation. We will be making choices as to how to represent a domain. Sometimes it may make sense to us to use such a constrained distributed encoding where all the values are 1 or 0. That might make sense when, for example, in our target domain, we understand a feature as being simply present or absent. We'll see examples of this as we go along. In such a case, then the possible vectors that we can represent are the corners of a hypercube. So if we have n bits, we just saw a three-dimensional case, we can represent 2 to the power of n. So in the three-dimensional case, 8 patterns. And the distances between patterns fall into a few discrete sets. This is a simple form of distributed representation that we might choose when our understanding of the domain is captured nicely by describing features as simply present or absent. The far more general case will allow all real values between 0 and 1 if we're restricting our inputs in that way. And that corresponds, each data point then corresponds to an arbitrary point within a volume. And their 2 given patterns in our data set may be arbitrarily similar to each other. We don't only have a few limited pairwise distances, we have very many. One of the big advantages that was perceived in early connectionist modeling was the use of distributed representations, which introduced some properties into these formal models that were not there under what we might call traditional good old-fashioned artificial intelligence modeling, in which symbols were used as the basic elements. So a data set in which the vector patterns have distributed representation has some properties that modelers might be interested in. One property that's often highlighted is the notion of graceful degradation. So consider a facial recognition program trained on a whole bunch of images of faces. If now a slightly degraded image is presented to the network, it will still perform fairly well. It can accommodate a great deal of noise. Whereas purely symbolic representations fail. They're very, very brittle if any noise is introduced. The rich capacity to characterize elements in our set as being similar or not similar is very, very important in order to capture important, continuously varying properties of the domain which is being modeled. And it allows us then also to fairly straightforwardly within our model interpret new data points to generalize beyond our training set, because the new data point will stand in a metric relationship to the data points on which the network has been trained. Some other properties that will be of less concern to us: content addressability means that when the network is trained on a bunch of patterns, its response to the pattern is not an arbitrary association, as it is, for example, when a letter is sent to an address. The address on the envelope bears no connection to the contents of the letter, but the response of the network to an individual pattern will depend on the content of the pattern. Networks that have been trained on specific patterns may be able, in the face of degraded input, to complete the pattern. If they have learned that a specific pattern induces a specific response, then a degraded pattern, again, or a slightly incomplete pattern, will tend to elicit the same prototypical response from the network. And importantly, we have a structural mapping of our domain in which the metric properties of the domain in the real world are hopefully reflected in the choices we made in our form of representation. Now, one thing you will have noticed about those distributed representations is they look like garbage for computers. They are not easily interpretable by humans. And we may find ourselves trying to understand a bunch of numbers, a bunch of vectors that a network has developed. Supposing, for example, we are interested in the hidden unit activations that a network has developed when being trained on a specific data set. A bunch of numbers are not easy to interpret. Sometimes we might want to see, for example, whether at the hidden layer, the activation patterns corresponding to the elements from our training set capture the similarity relations that we perceive in the real world. One way to explore this is to use hierarchical clustering techniques to make the relative similarity and differences among a bunch of vectors obvious. So in our training data, in our input patterns and in our output patterns, and particularly in our internal representations, the patterns of activation across hidden units, we often have this challenge that we would like to know how similar are two patterns to each other, or what are the, in general, can we plot the similarity relations within a large data set. There's a simple technique for producing a readily interpretable two-dimensional plot that captures similarity relationships among a bunch of vectors, even if the vectors have very many dimensions. This is called hierarchical clustering, and we'll be playing with it later on. And it's a very simple algorithm. Supposing we have a set of data points and we wish to understand their similarity relations. What we're going to do is we're going to incrementally build a tree that represents these. And the algorithm is going to look like this. We start with an empty tree and a full set of data points. Using something like the Euclidean distance metric, we can calculate all pairwise differences among the data points. So pair each point with all the other points, and then look among those for the smallest difference. we will use those 2 points that exhibit the smallest difference to add a node to our tree which we are building. That node will link those 2 points, and it will have a height proportional to the distance between them. So if they're very similar, the height of that element in the tree will be very small, and if they're quite dissimilar, the height of that element in the tree will be large. We'll see this graphically now in a minute. What we do then is we take those 2 data points out of the data set and replace them with a single point which lies halfway between them. So our data set just got smaller by 1 element, and we can repeat the process. Here's what it looks like. In this example, I'm using 2-dimensional data set, and I'm plotting a 2-dimensional tree. But I want you to understand that the tree is always going to be 2-dimensional, and the algorithm applies to input sets of arbitrary complexity, no matter how many dimensions we have. But it's easier for us to see what's going on if we use 2-dimensional data. So looking at the top left, we've got 4 data points. That would be 4 2-element vectors, A, B, C, and D. And I've plotted them so that you can see where they actually are, but in general, we will not have a plot like this available to us. But we can measure the pairwise distances between them, even if they're of 99 dimensions, for example. And if we measure the pairwise distances in this case, we'll find that points A and B are the closest together. So what we'll do is we'll start to construct our tree, as shown in the bottom right, by adding elements A and B and linking them by a structure whose height is determined by the distance between them. So A and B are 1 unit apart here, so I've drawn their linking unit in the tree as 1 unit high. Now we delete those 2 points and replace them by their midpoint, as shown in the bottom left-hand corner, and we repeat the process. So now you can see that when we do the pairwise distance thing for our 3 remaining points, the novel point and point C turn out to be the 2 closest elements. So we're going to add those to our tree, as shown on the right-hand side, where you can see C has been linked to the midpoint of the bar joining A and B. Furthermore, there was 2 units separating those 2 points, so this part of the tree is slightly larger. It extends the tree by 2 units. Now we only have 2 data points left. After replacing those 2 with the red midpoint, we only have that novel point and point D. So we'll simply repeat the process. What we'll do is we will join D to the CAB structure. There's 3 units separating them this time, so again the tree grows now by 3 more units. And so this is our result for that particular data set, and it makes obvious the similarity relations among these points. We can clearly see that A and B are going to be quite similar, and that there's a group around A, B, and C, and D is dissimilar. That was a particularly simple data set, and we will be experimenting with this in Lab 4, trying it out. Basic prop supports hierarchical clustering. Consider, if you will, a tree like this, if we'd grown it from a data set and we obtained a tree like the one shown. What would we say about that? Well, what we'd have to say about this particular data set is that the tree shows us that there are no inherent similarity relationships among the patterns at all. Everything seems to be as similar to everything else. There's no asymmetries, there's no structure there. So this might be the kind of tree we would get from, for example, a bunch of localist representations. So we'll be playing with that in Lab 4.